Y23 Lorentz transformation. Yesterday, we learned time dilation. That's the direct consequence of the fact that the speed of light is the same everywhere. In any inertial reference frame, speed of light is c. That results in the time dilation. A watch fixed on your wrist does not move. This is time multiplied by the speed of light, that is constant. Multiplication of c to time makes every component in, we will say, is for displacement. For displacement. This is not an adjective. That there should be a hyphen. No plural. No plural. It is a singular. For displacement. For displacement has four components. 3 Euclidean component and 1 additional component. We say it is a spatial component, the 3 spatial components that are Euclidean, and a single time component. After multiplied by the speed of light, every component has the dimensions of length. Usually, if an object is moving with a constant velocity, we use time t and velocity multiplied by time t. If this object is at rest, then means that speed velocity is 0. What I do is keep this spatial component to 0 and put special notation for proper time. The reason is that x mu, which is in general 4 vector. This is a Minkowski space. Minkowski space in which metric is the length. Length is defined by the time component square subtracted by spatial component square. That is a c tau square. This is invariant. That means ct square subtracted by vt square. This one is the same. As a result, we found that the time in general is proper time that is measured when v equals 0. However, if velocity of an object is non-zero, time must be modified in this way. And this multiplicative factor is gamma, and it is called Lorentz factor. And this Lorentz factor is 1 if v equals 0, and this Lorentz factor is greater than 1 for any non-vanishing velocity, and this Lorentz vector goes to infinity as v approaches absolute value of velocity, approaches speed of light, and v can never be greater than c. Never happens. using this one, we will find the length along the longitudinal direction. Longitudinal means the direction parallel to the relative motion shrinks. You can see there is a tunnel, the pipe or tunnel. And this tunnel, relative to tunnel and ball, red, this is a ball. If ball is at rest, standing still, v equals to 0, then this tunnel is moving backward with minus v. Relative to this tunnel, it is at rest. Red ball is moving with the velocity plus v. Understood? Any object measuring each other, the relative velocity is the same in magnitude and direction is opposite. Okay, this is how to measure the length of this tube. First way is to make use of proper time. How can I use the proper time? If you are standing on this red ball and you have watch, and you watch and red ball do not move at all. They are fixed. So the full vector is initially c multiplied by time. Starting time is 0 and position is 0. So you are at the origin here. You are still at the origin, and red ball, you and your watch do not move. So what you see is your watch, and your watch that is not moving shows the proper time. The difference is that the starting point, you just meet the tube at tau equals 0, and tube passes in this way with minus v, and at the end of the tube you measure the proper time. Your event, these are two events. Initially every component, the time and spatial components are all 0. At the end of leaving this tube, your watch shows tau. However, you know the relative velocity v. The tube is moving with the capital V backward. Now, you can say the length of the tube, length of the moving tube is relative velocity multiplied by proper time. And this length is moving tube. Moving tube. Okay? And the same event can be measured from here. At the rest frame of this tube, your friend is standing here and watch moving red ball. And this red ball meet you, your friend, at the same point. These are all the same, synchronized, the same, and origin are the same. But here, origin is fixed. And you're watching a moving red ball. I told you proper time tau is used only when the position is fixed. Right now, this red ball is moving with velocity v. Therefore, your space-time coordinate for the ball is CTVT. Instead of v tau. So we have Vt. That is what? Time t has passed. At that time, this red ball reached the point of L0. L0 is the tube length of the tube at rest. Ball is moving and your tube is at rest. Your friend is standing here. He knows the length already, and by the time t instead of tau, it reaches the other endpoint. Now, we can make use of the fact the flying object has time t, that t is gamma tau. Substitute L0 equals v gamma tau. Now, v tau is the length when it's moving. So we can say gamma times L. This is moving tube. And L0 is a rest tube. Rest tube, we say it is a proper length. Proper is attached everything at rest. Proper length. In comparison with the proper length, there should be gamma that is greater than 1. Therefore, L is L0 over gamma. And what's that? Square root 1 minus c squared v squared L0. This is less than L0. That means moving tube This is a rest tube. This is rest tube. The proper length of the tube is this. And when you see the tube moving, it is shorter than the original length measured at rest. That is the proper length. This says along the longitudinal direction, length is contracted. That is called the length contraction. That is exactly equivalent to the time dilation. Because of that, this ball is a sphere when it is seen at the rest frame. However, in the frame where tube is at rest, the ball is moving and the ball becomes thin. Sure, the cross-sectional area is the same, but along the direction of motion, its diameter has been shrunken by a factor of 1 over gamma. That is less than 1. So the length contraction is the direct consequence of speed of light invariance. So length contraction and time dilation, they are equivalent. we have derived this already. And time dilation and length contraction, they are not fake, it is a fact. And we use the GPS without considering this time dilation effect. GPS, geopositioning system we are using everyday life, order of 10 or 15 kilometers per day will be wrong. So it cannot be used commercially. But when you ride a taxi, if the map shows turn to the right 10 kilometers earlier or later, what's for? There is no way of no use to use the geopositioning system. So time dilation is not a joke, it's a fact. Let us consider the transformation matrix that allows us to, that realizes this transformation from this to there, or in opposite direction. That transformation matrix called the Lorentz transformation. First, we assume a 2x2 matrix. We know there are three directions, x, y, z direction, but the direction perpendicular to the relative motion is invariant. As you can see, the shape of a ball changes only along the longitudinal direction, and transverse direction is invariant. So we don't care much about the invariant quantity, and what I want to do is find out the longitudinal contribution and time contribution. We can construct the two-dimensional Minkowski space vector that is called the 4-vector, neglecting the invariant transverse components. A simple way to find out this matrix is by making use of the solutions. We know the time dilation is reflected in this representation. If something is at rest, only proper time flows, and if something is moving, then the time flows is not tau but gamma tau. This is a very strong constraint. We used the rotation of a unit vector to construct the cosine theta and sine theta. We learned that 0, 1 unit vector along the y-axis transforms into sine theta, cosine theta. Using this, we constructed the rotation matrix of the form cosine sine and minus sine cosine. Using a similar method, we construct the boost matrix, Lorentz boost matrix. Boost matrix means it generates the relative motion by velocity v. Okay. This transformation matrix must satisfy when it boosts up and down, go back to the original place, then you should get the identity matrix. Because relativity assumes the motion of one object and the other object observed by the other person is identical in magnitude, except that the sign is different. Here, there is a missing power, inverse, lambda inverse. Let me write it somewhere. All right. So actually, this one is C tau gamma, V tau gamma. And if I factor C tau, the C tau 10, and the other one, if I boost this one, C tau, what's that? C tau gamma and V over C gamma. So we will find V over C so many times. So we will call this beta, V over speed of light beta. So it is a C tau gamma, gamma, beta. Using this similar method, we find that 10 transforms into gamma, gamma, beta. That's this one. Okay? And the method, the inverse is obtained by substituting V minus V, replacing V with minus V. We can find that the other contribution is like that because one zero boost gamma, gamma beta. And what happens in the inverse case, 10 must boost 2 gamma and gamma beta with negative sign because gamma is independent of sign of beta. Okay, so as a result, once you obtain this Lorentz booster matrix, the inverse is trivial. Inverse is nothing but the replacement of beta with minus beta. All right, and then now we define the metric tensor. Metric tensor in Euclidean space, we remember this identity matrix was the metric tensor. Why? When we define the scalar product of the two Euclidean vectors, we put a vector as a transpose and the other vector as a standing up. So column vector and row vector multiply and substitute identity in between the two. And this identity matrix defines the scalar product in this way. Okay. However, in the Minkowski space, this scalar product does not is not invariant. Instead, we remember C tau squared subtracted by 0 squared equals CT squared minus VT squared. That means zeroth component subtracted by spatial component is invariant. So definition of a scalar product in Minkowski space is different from what we learned regarding the Euclidean space. Instead, it is a square subtracted by square. What can I do? It is in 4-dimension, time component is 1 and spatial component -1. But right now, we forget about the transverse component, and we are focused on the time and x component only. In that case, the metric tensor is like that. All right. So when we multiply two 4 vector in the Minkowski space, then what we do is 1 minus 1 minus 1 minus 1. Multiply them. These are not powers, but vector indices in Minkowski space. So we say it is a metric tensor in the Minkowski space. And actually, we learned that it is a Lorentz boost matrix is of this form, right? But let's see. Square subtracted by beta squared gamma squared. What's that? I can factor gamma. And by definition, gamma equals 1 over square root 1 minus beta squared. So this is nothing but 1. Aha! Something squared minus something equals always 1. Something squared plus something is always 1. What's that? A equals cosine and B equals sine theta. But in high school, you learned something squared minus something. Aha. Cosine. Cosine. Hyperbolic. Sine hyperbolic. That's 1. Remember? So this one can be expressed in terms of hyperbolic function. Cosine hyperbolic phi, cosine hyperbolic phi, and this one is a sine hyperbolic phi, sine hyperbolic phi. Okay, so boost matrix can always be parameterized in terms of hyperbolic functions. Just like what we have done with the rotation matrix, rotation by angle theta 1 and angle theta 2, you with respect to a z-axis, single axis, then you learn that what you have to do is just add the 2 parameters, angles, directly. So it is this. And this is also true in the boost matrix. Cosine, angle, sine, hyperbolic, and with another boost. So this is a boost, a series of boost, relative velocity v1 and relative velocity v2. This series of boosts along a single axis will give, if you multiply 2 matrices, cos, cos, sine, sine, plus, what's that? High school students know that it's a cosine hyperbolic phi 1 plus 2. And what about this term? This one multiplied by this, cosine, sine, sine, cosine. Haha, what's that? That is sine hyperbolic. And the other two are carbon copy of this and this. Finally, you will find this hyperbolic function, cosine hyperbolic function can be pulled out, and you will find it is tangent hyperbolic. What is tangent hyperbolic? It is just beta gamma divided by gamma. That is beta. Aha. Tangent hyperbolic is just like V over C. And you know, tangent hyperbolic is V over C. By the way, what is the hyperbolic function in detail? cosine hyperbolic phi equals 1/2 e to the phi plus e to the minus phi. Sine hyperbolic phi is 1/2 e to the phi minus e to the minus phi. If I boost the system very fast and fast again, even in the case I boost with the same factor by n times, what happens? According to this formula, I would get n times of phi. Then cosine hyperbolic phi is 1/2 e to the n phi plus e to the minus n phi. If a phi is a positive, it will disappear as n goes to infinity. As n goes to infinity, what I get is a leading piece. What is a sine hyperbolic phi? It again has the same structure. So what is the tangent hyperbolic phi? Tangent hyperbolic phi, tangent hyperbolic n phi goes to 1. You boost infinite number of times by a same relative velocity. Whatever times you multiply, your final result is tangent hyperbolic phi equals 1. What's that? V over C reaches 1. It cannot be greater than the speed of light. V can reach the speed of light whatever boost you may make. That's very, very important. The velocity cannot be added further to have a velocity greater than the speed of light. And the uninteresting hyperbolic formula you learned in mathematics is actually a great interest in our analysis for velocity addition. According to our previous analysis, tangent hyperbolic is V over C. So if you make use of the boost along the x-axis by V1 and in addition V2, the resultant velocity is V1 plus V2 for if you are happy with the Galilean transformation. However, in relativity, that does not happen. Instead, its a value, according to this our analysis, sum of the two velocities divided by something else. And even in the case you are flying with the speed of light, substitute c everywhere. What's that? 2 times 2. 2 divided by 2, it is 1. That means the speed of light. You boost with the speed of light twice, then the result is the speed of light again. Interesting. This is the consequence, a strong consequence of the relativity and velocity addition. And this is another application by making use of the length contraction. And please review very carefully. In your exam, this problem appears.